Originally, WEP was introduced to Wi-Fi to provide Wi-Fi with a level of privacy somewhat equivalent to what was found in wired LANs, and hence the name WEP. Because in wired LANs, there were cables that were providing some inherent security as signals were found inside the cables, compared with in the case of Wi-Fi where it is an inherently broadcast medium. However, it soon became clear that WEP doesn't even provide this level of security. And it's not so much in the cryptographic strength of RC4 itself. RC4 is the cipher that's used in WEP. However, it's more about certain other problems in the way that the keys are used. For example, one problem with key usage in WEP is that the same key is used for both authentication and privacy. Cryptographers consider this to be a very bad practice. You don't use the same keys for authentication and privacy. You should use different keys. So this rule of thumb was not obeyed. Furthermore, the lengths of the keys were not long enough. At first, WEP was just using 64-bit keys. Later, it was extended to also allow for 128-bit keys. However, of these 64 bits or 128 bits, 24 bits are actually coming from the initialization vector. This IV, or initialization vector, is often unchanging. Since 802.11 doesn't specify how frequently it should change, in some implementation it did not change and it was just the same fixed 24 bits. And even if it was changing, it might be a known sequence and known way of changing, and eventually it would repeat in a few hours in a busy network. Therefore, you only have effectively 40 bits, or effectively 104 bits in the case of a 128-bit key. You only have effectively 40 or 104 bits for your key. Then this key is used with the initialization vector, which is sent in clear text along with the message. So this is a very bad way of doing things because your key space is not large enough to sufficiently protect against brute force attacks. Then the key is also shared by multiple stations and the access point. This made collisions, which means repetitions of IV, even more likely, which made it easier for attackers to break the whole scheme. Besides the poor key usage, another problem is poor integrity protection. There is an integrity check value, or ICV, which is computed for every frame that's sent with WEP. And the idea behind such schemes, in terms of providing data integrity, is that it should be something that's not easy to compute. And when, let's say, an attacker modifies as little as even 1 bit in the crypto text, the resultant ICV should be difficult to compute. So the attacker cannot simply easily modify the ICV to provide a valid ICV if the attacker changes 1 or more bits in the crypto text. The problem is that the ICV that's actually used in WEP is a linear CRC32. It's not a cryptographic CRC. So it's easy for an attacker to modify 1 or more bits in the crypto text and then to correspondingly modify the ICV so that it becomes a valid one, and thus this nullifies whatever integrity protection might otherwise have been offered by this ICV. A third problem that WEP faces is that there's no replay protection. There is simply no sequence number in the frames that are sent, and so the receiver has no way to tell whether a frame is genuinely being transmitted by a transmitter, or whether it's being replayed from something that an attacker heard previously being sent. This has resulted in many different attacks on WEP. The key stream can be discovered through a passive attack that's waiting for IV collision. IV collision refers to finding two or more frames that use the same IV, initialization vector. Because then we can XOR two frames with the same IV and the same key, and then we get the XOR of the two plaintext messages. Since XOR, when you XOR something with itself, then everything becomes all ones. So this effectively removes the encryption, and you have the XOR of these two plaintext messages. This allows us to do statistical analysis to recover the actual plaintext. Furthermore, such statistical analysis works better as the number of frames with the same IV increases. And there are variations where if we can somehow get some known plaintext to be encrypted and then sent, perhaps coming from a friendly website, friendly to the attacker that is, then the AP might encrypt that and it goes over the air, and the attacker can get more information more quickly this way. Besides that attack that I just mentioned, there are others as well. There's numerous attacks actually that have been proposed over the years. Another one is a passive attack to guess the key. There are a number of these. Perhaps very famously, we have FMS, which is based on weaknesses of RC4 and knowing the IV. Another one is Correct, which improves on FMS. And then PTW, even better. Generally, with FMS, you need about 6 million frames before you can recover the key. With Correct, you only need about 200,000, and this number drops to 60 to 70,000 with PTW. Besides the passive attacks that we've talked about, there are also active attacks that can be used, which can speed up the time needed to break WEP. So if we can actively inject traffic, then we can do things like chop chop, where we have fake ARP, and we can do things like the fragmentation attack. We can guess a few bytes from similar headers, and then we can recursively send fragments that the AP would combine and then send them back to the network to get more of the key stream. Partly as a result of the problems encountered with WEP, and also out of a desire to add additional layers of security, some additional security-related measures soon emerged. These predate better improvements like WPA, WPA2, and 802.11i that we will talk about in subsequent videos. But their emergence was a sign that the industry was trying to find some patches for Wi-Fi security, and also a sign that the Wi-Fi market was growing very healthily and robustly and quickly. In general, these measures were not modifying WEP, and the 802.11 specs are still followed, but these are more like workarounds in the implementation of Wi-Fi. They are by no means the best ways to patch the problems that came with WEP, but could be thought of as symptoms of the underlying disease, the disease of poor security, and the industry was trying its best to improve the situation. 3 such measures are listed here on this slide. Firstly, hidden SSID. Typically, an access point would be continually broadcasting its SSID. So, for example, if you have your laptop and you just do a scan, your laptop will show you SSIDs of Wi-Fi access points that it can hear around you. So you might have a few dozen of these that you see in your laptop. That's because your Wi-Fi network interface card is able to see these as they are being broadcast by the access points. Now, what if we don't broadcast the SSID? Then it's harder for attackers to know about the existence of an access point and SSID. The stations that are actually meant to be part of this network, we can argue that they should already know what the SSID is. They don't have to hear it from the access point. So then they can send the SSID and receive a response from the access point, whereas attackers might not know what the SSID is. And therefore the SSID becomes something like a secret password. However, this is not really very secure because there are other ways for attackers to find out the SSID of a Wi-Fi network, but still it's better than nothing. It does have the disadvantage though that if you want your network SSID to be visible by people using their laptops nearby, then it would not be visible. So depending on your setup, whether that's a pro or con depends. The second thing on the list here is MAC address filtering. In some of the early systems without WEP, only open systems authentication can be used. In this case, the station sends its MAC address along with its request. So the access point can check to see if this MAC address is on an approved list or on a reject list, depending on how the MAC address filtering is set up. And then it can either approve or reject this request depending on the presence of the MAC address in one of these lists. If MAC addresses were indeed unique and unchangeable, then this is certainly a good measure that will definitely work. However, it's possible to change a MAC address. So an attacker could figure out a MAC address that it knows will be acceptable, and then it can change its MAC address to that MAC address in order to get in. The third measure we see here is browser hijack, which takes the philosophy that Wi-Fi security is lacking, but this is happening at physical and MAC layers. So the philosophy behind the solution is that instead of trying to fix things at the lower layers, it just applies security at higher layers. It gives up the desire to try to solve things at the lower layers and just goes with securing things at higher layers, such as the transport layer. Browser hijacking is not a standard or specific way of doing things, but it's more of a concept, so there can be different implementations. Here is a typical way it might be implemented. We have a station trying to access a network. It does some kind of weak authentication with the access point, perhaps web-based authentication, and then it associates with the access point. However, the access point is keeping track of which of these stations have just joined and have not yet been further authenticated using something more reliable at the higher layers. So the first time that the user of the station tries to go to a website like google.com, for example, the access point will know that the station has not yet done the higher layer authentication and would redirect this HTTP request. So instead of going to google.com, it goes to an access controller. So this is a key step here, and it's the reason for the name browser hijacking. You're hijacking a browser session that's meant to go somewhere else like google.com, and you're bringing it to your access controller where you can then get the user to be authenticated, perhaps getting a user ID and password from the user. And in fact, that might be all that it needs, and then it can grant access. There are different variations. So in this diagram, we see a variation where the user name and password from the mobile might then be actually authenticated by some authentication server somewhere else, as we see here, the home network of the station. But this is just one of many variations. The key idea behind browser hijacking is this redirection here of the initial HTTP request. So the access point needs to keep track of who has already successfully been authenticated at the higher layers and who has not.